Hello.
So my name is Jitendra Pandey. I work for Hortonworks. I've been involved with Hadoop and its ecosystem for 5 years now. And this is my friend Gopal. He's also at Hortonworks. So starting now, so around 1 year back, we started with this project called Stinger Initiative. And this was to address speed, scale, and SQL in Hive. And this talk will be primarily focused on speed. And in speed, the key area of focus was the query planning using a cost-based optimizer which uses data statistics, then better and faster execution. We introduced a new execution engine called Tez, and which provides much better parallelism, much better scheduling, and also helps generate better plans. Then we also invested in improving the query setup time, query startup time, and also on the I/O path. So statistics are collected in Hive. We have table-level statistics. We have column-level statistics. And a cost-based optimizer is based on a framework called Optic, which is an open-source system already being used in many other systems. It is based on the traditional Volcano paper, and there are a lot of developers are working on it as well. So the key areas where this statistics and cost-based optimization is being used is to determine the parallelism dynamically, to determine the right join selection algorithm, to determine the join ordering, and Tez vertex boundary selection, which essentially means that how much compute can we put in a single Tez vertex and how to distribute it across different vertex. I'll give an example of this in later. So this query demonstrates how we are using cost-based optimizer for join ordering. So here is a query. We have 3 fact tables being joined together with bunch of dimension tables. And you can see that there are 3 dimension tables being joined to table SS, and then 1 for 2 other dimension fact tables each. So a non-CBO plan does a pretty naive join ordering where it joins the 2 fact tables, being shuffle joins the 2 fact tables, and then being joined to another fact table. And then dimension tables are joined later on, which is not the optimal order of joining. And a CBO plan basically pushes a dimensional join to one of the fact tables much earlier, and that reduces the amount of data being shuffled and for the later join. So this table shows that how much, what cost calculations went in. You can see that the 2 fact joins, store sales and store returns, are much more expensive, and that's why they were dropped. But the dimensional joins provide much less cost, and therefore the one with lowest cost was picked up. And the query runs also show around 2.5x time improvements. And there is a brief note about the bucketing. If you have a bucketing enabled, that also helps CBO join because the CBO join will reduces the amount of data being shuffled, so we can use a partitioned hash join here. One thing I want to mention is that this cost-based optimizer code is out there on a Jira. It's not yet committed to Hive trunk, but it will be committed soon. Now introducing Tez, you must have heard a lot about Tez. Tez is a DAG-like computation engine where you can express your computation in form of DAG, which has vertices and edges. Vertices represent the processing, and edges represent the data flow. So it has been already Pig and Hive and Cascading. They are trying to use Tez as the primary execution engine underneath. So we will go through some of the queries and how their plan looks in the Tez and compare it with how it looks in MR. So and that's how we will demonstrate that how Tez plan is a better plan. So you can see that this is a query which joins the output of 2 subqueries, and the 2 subqueries themselves are simple group by queries. A Hive-on-MR plan runs 2 MapReduce jobs to generate the output of the group bys, which the data is put into HDFS, and after that there is another MapReduce job to do the join. Again, the data goes to HDFS, then another MapReduce job for the order by. And Hive Tez plan does this in much less number of stages, and does not write to HDFS in the intermediate stage. One of the group bys produces output in a MapReduce job, but that output is streamed to the reducer of the other group by, and the join is done there itself. So which really cuts one of the processing stages. And there is a final reducer that just does the order by. So another example is a shuffle join. So here these two plans look pretty similar, but there is a key difference that the mappers in the Hive-on-MapReduce plan would actually process both the tables, and so that their partitions could be co-located on the reducer. This restriction is not there on the Tez side. Tez, the mapper just focuses on one table, and the Tez framework makes sure that the partitions are correctly positioned on the right vertices. And the advantage is that the mapper is much simpler because it's dealing with a single table, and also it doesn't have to switch between the data paths, which is more efficient. Now, one of the key implementation differences between MR and Tez is this introduction of broadcast join, which is basically a new map join implementation. Map join is another name for hash join that we use in Hive. So in this case, we see that a table, there is a small subquery which is being joined with a inventory table, which is a sufficiently large table, and a Hive-on-MR plan is a usual multiple MapReduce stages plan, in which first MapReduce stage processes the subquery, and the second MapReduce stage does the join. But in case of a Hive-Tez plan, the first stage does the group by, but its output is directly broadcast to the second stage of the mappers. Now, this broadcast essentially means that each output goes to all the subsequent mappers, and this broadcast edge avoids writing data to HDFS, which I've already mentioned before. Another advantage of a broadcast join is that it achieves much more better parallelism. In case of a map join, in an MR plan, the hash tables are calculated on the client, and those hash tables are calculated sequentially and loaded into HDFS. But in broadcast join, they can be calculated across the cluster, achieving better parallelism and also better data locality. This 1-1 edge is an additional flexibility that a Tez plan can provide. The idea is that suppose you have a star join, and now you want to join multiple dimension tables to a single fact table. Now, each dimension table may be small enough in size, but all dimension table put together may not fit in a single mapper task. So Tez allows you to split this processing into multiple vertices where first vertex joins a subset of the dimension tables, and second vertex joins another subset. Thus, Tez will allow you to do a pipeline of in-memory joins, so which was not really possible in a Hive-on-MR plan. Dynamically partitioned hash join is another implementation for the bucket map join that existed in MapReduce, but bucket map join had many limitations which are not there in case of in a Hive-Tez plan. First of all, the Hive-on-MR needed both the tables to be bucketed. And then one of the tables, the hash tables for each bucket would be calculated on the clients, then loaded onto HDFS. And then for subsequent processing, you can only launch as many map tasks as the number of buckets. Now, these limitations are gone with Tez. The hash tables for each bucket can be parallelly computed across the cluster, are streamed to the mappers on the subsequent stage. And this streaming is a broadcast-like streaming, but it uses a custom edge because you have to pinpoint which bucket goes where, and then subsequent stage does the join. So another key advantage is that suppose the tables are not bucketed to begin with. In that case, Hive-on-MapReduce would just do a shuffle join. But with Tez, if only one of the tables is bucketed, we dynamically bucketize the other table and do the bucket partition hash join. Another advantage is if none of the tables are bucketed. But if the query has some previous stage of processing which is forcing the bucketing. For example, if there is a group by, and that group by causes a bucketing of the data, then the subsequent plan can take advantage of that and perform the partition hash join. So this is a very key advantage. And another thing is we are not restricted to the number of mappers. I mean, one mapper per bucket. That restriction is gone away. The bucket can be processed across multiple mappers. So that is why a dynamic partition hash join performs much more efficiently than what it would do in an MR mode. Then this union all example is a almost repetition of what we have before, what I've talked about, that you have two subqueries and we want to do a union, and in an MR plan you can see that there are two separate MapReduce jobs, output loaded to HDFS, and then a separate MapReduce stage. And in a Hive-Tez plan, it is a simple DAG where the output of the two subqueries is streamed together. And the last example I have in this mode is about multi-insert queries, where we have a subquery which is a join in itself, and now we want to run two selects on it which end up populating two different tables. So here again, the MapReduce plan, you see, has to write the intermediate data to HDFS, and then we need separate MapReduce job to run the two select queries, which is completely unnecessary because those two select queries are working on the same input. So the Tez plan looks much more efficient and optimal. Of course, this kind of plan reduces the amount of I/O and also reduces the amount of data that that is flowing through the network. And so this concludes our work on the planner side, and there is a lot of work that happened on the query execution. I will invite Gopal to talk about that.
Hi. So from what you have seen earlier, you might have noticed that for a lot of the plans that you saw, the plans between MR and Hive look logically identical, right? So even though the plans might look the same, that one is writing to HDFS, other is shuffling directly through, the massive improvement in efficiencies that we have got with the new plan is thanks to the fact that we can actually execute things earlier and more optimistically in Tez than anything else. So let me go back a little bit and start with how we actually start a query, right? So the way an MR task starts a query is by first spinning up what is known as an application master, which owns that query. So for every query that you run, you have an application master. And I should not say for every query. It used to be for every job of a query, you had an independent application master. So if your query had like 4 stages or 5 stages, each of those stages was started by a task on yarn that spins up, which becomes a master for that particular section of the job. Taking that out and making sure that one application master takes care of the entire query basically means that an application master not only knows what it's doing, but what is going to come up next. And knowing what is going to happen after this particular task completes is a huge advantage when you actually are trying to actually run this in a very fast way. Second part, I think Jitendra talked this a little bit about how we do not have local tasks anymore, right? And the fact that we do not have local tasks might not seem a big difference if you're running one query at a time, but if you're running a production system where hundreds of people use the same machine as a gateway node, you would realize that that machine becomes your significant bottleneck in the cluster, right? So being able to take the task that you would have run inside Hive client and running it inside the cluster gives us a huge benefit if you use a server JDBC model like HiveServer, because you no longer have to provision for a cluster of Hive servers because of your CPU limitations. And secondly, if your local task consumes a large amount of memory, you don't have to actually worry about affecting your server performance, right? Your edge node that everybody logs into and runs queries is not slowed down because the small tasks are memory hungry. The other improvement that we've made in Hive 13, and this is completely independent of everything else, is that we added the metastore accesses, a fast path for metastore accesses, which actually skips a lot of the old code paths for metastore accesses and specializes it so that it is faster for MySQL, Postgres, and Oracle metastores. So that we are no longer limited by the lowest common denominator of metastores we use, which is Derby, so that the calls that we make to metastore are really, really fast. There is a big reason to actually do that, because I don't know how many of you went to the Yahoo talk. They said that they hit a limitation where they hit 1 million partitions in a table, and they had a bottleneck. So for stuff like that, the metastore was actually sped up so that when a query starts running in 4 seconds on Tez, you do not want the query to spend 2 seconds actually fetching all the metadata information, right? It became a significant fraction. So the metastore was sped up. A lot of the partition filtering, like if you wanted to pick a particular date out of a large table, the old mechanism was to actually pull in all the partitions and go through them and filter out what you don't need, right? Like now we can actually pretend that we are going to just push this part to the metastore and make sure that a large number of the partition filters are run on the metastore so that it doesn't move over the network. This made the metastore faster and plus allowed us to put more stuff into the column statistics and layers in the metastore without actually affecting any performance, because for the cost-based optimizer, the amount of statistics you need to fetch is per partition, which is huge. The next thing we did in terms of query setup is that Hive used to submit a job jar with every request, with every job it ran. This is sort of a MapReduce holdout, because MapReduce, you submit a job jar and you get a result, right? Whereas in the new model in Tez, we actually do not localize anything, and we accept something that is sitting on HDFS already as a path. So you do not actually end up downloading any jar files for a Hive query that you ran that is supposed to take 1 or 2 seconds. This is not very significant when you are actually dealing with a cluster with 20 or 30 nodes, but when you're actually trying to scale it to 350 or 450 nodes, trying to get a new jar file to all 350 nodes is a significant cost to your latency. The way we used to do this before was to set the replication to 10 and do, like Hive had code to do that. We no longer have to do any of those things anymore, which is great. The next thing is people use Hive over other SQL solutions because Hive supports a large number of UDFs, right? And in terms of supporting UDFs, not having to keep uploading them again and again and again for every add jar is also a huge win here. And lastly, a lot of the stuff that used to use XML in the last Hive releases has switched to Cryo, which is faster. Next part that was slow in the runtime section is actually running the operators, right? So this is a dump of the assembly generated by JDK7 of a method called expression node evaluator. And you can see that some of the stuff there is highlighted in red, right? Those instructions are actually there simply because we perform a type check, right? We're trying to make sure that these 2 arguments that I've got are of the right type, right? Which is almost completely irrelevant, because in Hive, you're almost guaranteed that if you're querying an integer column, it will always remain an integer column. It is not going to change type to float in the middle, right? So to take advantage of this, we added the features that we did with vectorization, with the knowledge that types do not change at runtime, to produce independent operators for each comparison that you had to produce. So there is code in Hive when you build, which goes through all the operators you have and generate type conversion and type comparison operators, so that comparing an integer column to a constant value produces different code and faster code than comparing it to another column in the same system. So along with this, because you're suddenly reading type values, you can decide to use integer, I shouldn't say integer, primitive ints of integer objects. And the huge advantage of using primitive ints is that putting them in an array makes it actually contiguous in memory. An array of integers do not actually exist in memory in Java as a sequence. It actually exists as, here is a sequence of pointers, they will be somewhere in the system, somewhere in your Java heap. So you couldn't optimize that no matter what you wanted. With an integer primitive array, you could guarantee that if it was less than, say, 4 KB, it would actually be contiguous in memory, which meant that you could make sure that all the loops that you're running are small in the instruction cache because they're for only one type, are small in the data cache and fit into your data cache immediately because there are 4 KB and they're contiguous. These two things make a huge impact to something like TPC-H Query 1 and Query 6, which massively do a large number of filters. Like Query 1 in particular becomes 3.5x faster if you turn on vectorization and the per type opcodes, right? When you run the same code a million number of times, the JIT also actually gets better. The moment it understands you're always going to add 2 integers here, it just replaces all the inefficient Java push, pop, bytecode with efficient register operations. Next part, the file format. So we found that RC file, which is what people used to use, had significant limitations in a lot of ways. One of the things that RC file had was run length encoding, right? RC file had run length encoding built into it, saying that if a column repeats, store it, that the fact it repeats. But we had no way to actually read it out. And we did not have a way to actually do something like a dictionary compression. So what ORC brings to the table is a bunch of logical compression operators, string dictionaries, delta packing, RLE, and then actually adds a layer of zlib compression, which takes most of the advantages of RC file and gives us something extra. The next part it actually does well is that it generates splits very, very efficiently. That you will never have a map task which reads 0 bytes. With RC file and old combined input format, you couldn't actually get there. And on top of that, we have predicate pushdown, which means that you can say that only deserialize these 10,000 rows if any of them, if at least one of them matches all criteria, right? You don't have to deserialize one row, check it, and then decide whether to deserialize the next row, which is sort of what the lazy deserialization did before. And on top of that, the ORC footers gave us a place to always make sure that whenever an insert happens, we keep track of min, max, and count of the table, or at least that file. This meant that when we wanted to calculate statistics, particularly column statistics for data, we could actually collect it by just reading like 10 or 15 KB of every file instead of scanning through the whole data set. Plus, if you knew, and if you're looking for anomalous data, you could exclude entire chunks of files very, very quickly. Like the query that you're seeing there is as a flat inserted store sales table from TPC-DS, which is about 10 TB big, and I'm scanning through it in less than 2 seconds. And I'm scanning through in less than 2 seconds because I'm only reading like 15 KB of data from it. Because I look at the date, and the date says all the date, the min of the date is 0, right? And it obviously tells me that I don't have to read that file anymore. So being able to store that information within the file basically means that whenever an insert happens, it will always be kept up to date, which is something you cannot enforce in the other parts of the system. Because if you do any kind of ETL, you have an external table. Last part, or the most important part everybody talks about, is Tez. And the reason Tez makes things faster is also because it specializes. It says that here is these different things you can use. You can pick in the Hive plan which one is suitable for which, right? And the broadcast, shuffle, and one-to-one edges that Jitendra talked about before can be mixed with the fact that they can be sorted, unsorted, or partitioned. Of course, partition doesn't make sense for broadcast edges till now, but it still has a huge advantage if you actually want to do a broadcast map join, which is to chunk up a map join into 4 or 5 equal parts and send it to different places. Lastly, when you build such a large graph of vertices to run your queries with, it used to be that applying one configuration across an entire set of vertices you have was not very efficient. So the other thing that Tez brings to the table is to be able to say that for this vertex, these rules apply. And to say that for the next vertex, those rules do not apply. And this means that you can also optimize and send that for a given vertex, I can only send it the operator plan for that vertex. I do not have to send all operator plans for all vertices to everything, right? Like I don't have to communicate the whole plan to the first vertex. On top of that, once you've read data from disk and processed it, you have to give it to the next task, right? Tez split apart the significant parts of MapReduce out of the installation of Hadoop. Like it made it a client library instead of something you install on a cluster. Since you don't have to copy the Tez jar to every machine or run anything on any machine, it basically means that we can innovate on Tez way faster than we can innovate on something that requires complete replacement of a cluster just to go to the next version. Which meant that we could actually put in things like the keep alive shuffle, which is trying to connect to a node once from a reducer, so that if you have 20 nodes, the maximum number of connections any node will get is 20 instead of getting 200. And to make sure that when container use kicks in, these keep alive sessions actually speed up everything. When you're trying to talk about a query that has to go from 7 seconds to 4 seconds, these small details are what actually makes a large difference. Then we looked at a bunch more queries and found out that a lot of people had queries where they would estimate that they need 700 reducers, and about 20 of them would get actual data. In the old MR model, most people got away with this by setting the number of reducers. Like if you look at, say, AmpLab benchmark, you'd find that they actually set reducers to get the best parallelism out of the system for Hive. But in the Hive 13 plus Tez scenario, we don't actually have to do that because it will estimate, and if it estimates wrong, it will correct it in the middle of running the query, right? I don't know how many people can read the graph there, but it goes from 2018 reducers to 289 reducers after it finishes about 25 or 30% of the map tasks. And even this configuration can be set up per vertex. And ideally, the ideal scenario would be to make sure that you get per partition information, so that if you know that partition 1 is 200 MB, and partition 2, 3, 4, 5 is 200 MB, you would split them into 2 reducers, so that all of them would get fair amount of data. So the minimum skew would get is how big one single key is. We haven't gotten there yet, but this is a good step. And the other advantage that auto-parallelism brings about is the fact that if you had 200 containers in your cluster, like a 20-node cluster, trying to start 999 reducers will basically mean that only the first 200 startup, or say 190 startup, while the other 10 map tasks are finishing. So about 700 of your containers, 700 of your reduce tasks have not gotten a chance to do the slow start operation, right? And if the first 200 are not the ones getting a lot of data, then this actually slows down, because until the last mapper exits, the reducer cannot say that I never got any data, because the last mapper could be giving data. So this reducing the number of reducers actually makes things faster, because the tasks that actually get data can get started first. And hopefully all of them run within your cluster. So let's go to looking at the queries that we run. So this is a query where each lane represents one container. And obviously, we are not counting any of the stuff we do to count the splits, spinning up the AM, or uploading the jars in this particular diagram. We basically start off the local task immediately in the cluster. And in this case, we are only running one per local task, but they start off. And they start off the moment their splits are calculated. And the old Hive model, you would have to calculate splits for everything before you start off a query. Here, the moment the splits of the first thing is calculated, it can actually start processing, asking for resources. So basically, you can jump in front of the yarn queue the moment you have splits for at least one task, right? You don't have to wait for all your tasks or all your inputs to be ready before asking yarn that I need a container, because you already know. Then the predicate pushdown that I talked about kicks in and goes through a bunch of the files to see that are there any of them I can completely ignore, so that I don't ask for a container on a machine and then later find out that I don't need any data from it, right? This is basically a nice feature because it gives other people the opportunity to run stuff on the cluster. Because you might start a container and kill it in 3 seconds. Those 3 seconds you can never get back, right? CPU time is like bandwidth. If you don't use it for 10 minutes, you can't just get it back. The pipelining of split to task basically means that the moment you have a split, you can fire it off at a task, and hopefully by changing, once Hive-on-Tez becomes the standard way of Hive execution, we can actually add more information to this so that parts of the big table can also do the pipelining operations. So that you can calculate half your splits, fire them off, and then keep calculating. This matters when you have 1 million or more files, because that is when the actual getting into the yarn queue is slower than calculating splits. Right? Until then, it's mostly you can wait 2-3 seconds in the other part, so you don't get a lot of benefit from this. The other part is that you try to fill the pipeline as tightly as possible, in the sense that you do not give up a container quickly if you can't use it again. So you can see that the local tasks and the main task runs in the same container. This basically means that there are 3 few yarn requests sent to the resource manager, which is better for the resource manager and for the query. And the ORC split generation that I earlier talked about, which actually lets me figure out exactly where the split boundaries are. So which basically means that I will never have an ORC split which crosses a machine boundary. Either I'll have 100% locality, hopefully. In this case, I seem to have 100% locality. Or I will have a remote read. I will never have a case of picking a compromise where I pick a machine which has 50% of my data, right? Then we have container use, which uses the same container to run multiple queries, to run the parts of the same DAG, parts of the multiple queries. And as you keep running more queries in the same container, it actually gets faster because the JIT gets better and better at recognizing the common patterns you use and starts optimizing for code paths you never take. The most classic example is debug logging. If you've got a debug login, it will try to remove the debug log and put a what is known as a common code path, not a common code path breakpoint, so that when it hits that part, it knows that it has to go re-execute this function with the less optimized version. So as long as you don't hit that code path, it's way faster. If you hit it, it's slightly slower. But when it comes to debug logging, I prefer the faster always option. Now, this session stuff used to work only for one Hive shell. With HiveServer2, we can actually take one session from the same user and give it to the same logical user again. This makes a huge impact when the new SQL authorization model came up, because every query runs as Hive after authentication, right? So it doesn't matter whose session you're giving to anybody. Everybody has the same access control. And as you can see, that query is taking 5.5 seconds. So this is really, really great when you're looking at short queries, because for something like Tableau or MicroStrategy, you can get in and get out in like 4 or 5 seconds for a couple of 100 GB easily. This is query 4 from TPC-DS. I do not see anybody benchmarking this query, because it is the most monster vertex query if possible. So I tested this with container reuse and all those things to stress out the system and try to figure out how much of, whether we have any memory leaks or any such problems. Most of it is gone. Rest is UDFs. Everybody audit your UDFs. And try to run hundreds and hundreds, 5,000 queries in the same session container to see how scalable the sessions are. They are also scalable. Even the application master got faster in this scenario after a particular point, because it was shuffling so many messages that it got better at passing messages. So over the last year and a half, we've gone from a query that most people look at in text form in comparisons to something that takes a graph that I cannot actually show, like 4.5 or 4.8 seconds. And we sort of looking forward to expanding on the cost plus optimizer, trying to build temporary tables and materialized views in Hive. And temporary tables make an impact in scenarios where you want to feed back statistics of what you want to do, like a distinct query that you're going to use everywhere in the session. And do a bit of the join group by stuff without actually sorting data, like not without actual comparisons. And SMB joins, which is probably the fastest way to do joins if your data is sorted. And try to do a distributed order by, which can actually do order by with multiple reducers, which probably doesn't affect things like TPC-DS where there is almost always a limit, but for customer queries you need all the data sorted, it does actually make an impact. And Tez lets you do that. That's all I have. Questions?
Hi, I have a question about the ORC format.
Yeah.
Basically, my background is primarily relational databases,
Yeah.
column stores and things like that. And your mileage may vary, but in my experience tuning the queries, usually I get most bang for the buck by eliminating I/O.
Yeah.
So in a columnar database, we store columns separately,
Yeah.
and we reconstitute records after we run the query.
Yeah.
And by storing the columns separately, we can do a lot of performance optimization, eliminate a lot of I/O.
Yeah.
Is ORC storing the data? Is ORC a smarter version of our C file, but fundamentally different columns are still in the same HDFS block, or are they stored truly separately?
They're stored in the same HDFS block for a very good reason. It's because we want to avoid cross-machine I/O.
I see. So if we want to reassemble the record remotely over network, that would never work well.
Yeah.
And Hadoop block allocation policy does not allow us to enforce any kind of locality.
Yes. Also, if you had a table with 600 columns, you would find it very difficult to write 600 files for every partition. That's
true. There's ways to cope with that in columnar databases, but so is there any plan to support this type of columnar format like columnar databases do, maybe by tweaking the block allocation policy or allowing to read part of the HDFS block rather than the whole block?
We actually allow you to read part of the HDFS block. So the data I/O from disk is actually columnar, but within a file.
I see. So you read part of the block and eliminate the I/O.
Yeah, and that is, you can actually do it zero copy. So.
All right, cool, thanks.
Thanks, Jitendra Gopal. Interesting session there. I had one doubt, more like the question. In principle, what you're doing in Tez, you're eliminating the HDFS intermediate write, but doing the streaming process there.
Yeah.
So in principle, it does not have to do anything with yarn. You could as well have that same functionality done in the traditional MapReduce as well.
Yeah.
To improve that kind of functionality and gain the performance there. That is one thing, but you did also mention that at some point of time, do you have an upper bound where it would not work? And you mentioned that the streaming processes you can have in sequence in case you need to optimize that further. So can you?
So if you had something like 10,000 nodes, the scheduling algorithm that you would use would be very, very different from what we do now. If you have 3,000 nodes, it would still work. But it's like n square of sorts if you completely connect them up.
Yeah, but in principle, it has nothing to do with yarn, right? The whole thing I can replicate in the MapReduce traditional way, and I can get the same kind of performance uplift, right?
Yeah.
Yeah, and the other thing is, you mentioned something like streaming in parallel, or some streaming process. Jitendra mentioned it, so I did not get that.
We can talk later.
I think we
we're
are out of time.
Okay,
we can
sure.
address it
Sure.
offline.
Thank you.